All right. If you've ever hit a wall in your calculus or differential equations course, staring at a problem that looks almost linear but just isn't, then you've probably met a Bernoulli equation. In this explainer, we are going to completely demystify this thing and give you a rock-solid method for solving it. Let's get right into it. So first things first, what exactly is a Bernoulli equation? Well, it's a first-order differential equation that has this very specific form you see here. Now, take a look at that n up in the exponent. If n was 0 or 1, hey, no problem. That's just a standard linear equation we already know how to handle. It's all those other values of n that make things interesting. And that's the heart of the issue, right there, that little y to the n term. That's the one thing that messes everything up, that breaks the linearity and stops us from using our usual bag of tricks. It's kind of the villain of the story, but like any good villain, it has a weakness. So how do we deal with a problem like this? We don't try to fight it head on. Nope. We need something a little more clever. Think of it like mathematical judo. We need a secret weapon, one that can change the entire game. And here it is. This one little substitution is the entire key to unlocking this puzzle. By creating a new variable v and setting it equal to y to the power of 1 minus n, we can literally transform the entire equation. This single move takes that scary, non-linear mess and turns it into a friendly, familiar linear equation we can actually solve. And you know what the best part is? This isn't just a one-off trick. This substitution lets us build a simple, repeatable process, a 5-step recipe, really, that's going to work every single time you see a Bernoulli equation. And here's that recipe, laid out nice and simple. It's our 5-step roadmap. First, we divide everything to get that pesky nonlinear term on its own. Then we bring in our hero, the substitution. That's the magic step that transforms the equation. From there, it's pretty straightforward. We just solve for our new variable v, and then finally, we substitute back to get our real answer for y. Okay, enough talk. Let's see this recipe in action. We'll start with a classic. Y prime plus y equals y squared. You can see it fits the Bernoulli form perfectly, and in this case, our troublemaker n is equal to 2. So, following our recipe, step 1, we divide the whole thing by y squared. That gives us this expression right here. Now for step 2, the substitution. Since n is 2, our new variable v is going to be y to the power of 1 minus 2, which is just y to the minus 1. And because we have a y prime in our equation, we're going to need to figure out v prime. A little chain rule action tells us that v prime is negative y to the minus 2 times y prime. And here we go. This is the aha moment. We can now swap out our y terms. That whole y to the negative 2 y prime chunk, that just becomes negative v. And the y to the negative 1 term, that's just v. A quick bit of rearranging and look at that. What's left is a perfectly clean first-order linear equation. The nonlinear problem has literally vanished. Now for step 4, solving for v. We just use the standard integrating factor method for this. We're not going to go through all the nitty-gritty of that here, but after you run the numbers, you find that v is equal to 1 plus some constant c times e to the t. And finally, the last step of our recipe, substitute back. We know v equals y to the minus 1, so we swap it back in, do a little algebra to solve for y, and there you have it. That's our final, clean solution to the problem we started with. Okay, that was a pretty straightforward example. But you might be thinking, sure, that works for the easy ones. But what happens when the problems get messier? What if we have variable coefficients instead of simple constants? Great question. Let's take a look at this tougher case. Yeah, it looks a lot more intimidating with those fractions and x cubed terms. But hang on, look at the most important part. The term on the right is still y squared, so n is still 2. The fundamental structure is exactly the same. And because the structure is the same, our recipe works just as well. We use the exact same substitution, v equals y to the minus 1. We go through the same transformation steps, and sure enough, it spits out a linear equation. Okay, the functions themselves are a bit messier, but the process, identical. We solve for v, and we're on the home stretch. We back substitute for v, solve for y, and boom, there's our final answer. See? The recipe handled those variable coefficients without even breaking a sweat. Let's just put them side by side for a second. Our first example had nice, simple, constant coefficients. The second one had those more complex variable coefficients. But even though the functions looked totally different, the 5-step process we used to solve them was exactly the same. That's the real power of this method. All right, let's throw one more curveball. This next example has two new challenges. First off, it's not even in standard form to begin with. And second, look at the term on the right. It's y cubed. So this time n equals 3. But it's no big deal. Our very first step is just a little algebra to get it into that standard form we know. Now, since n is 3, our substitution is v equals y to the 1 minus 3, or y to the minus 2. We follow the exact same process. Divide, substitute, and just like clockwork, the whole thing collapses into a new linear differential equation. We solve that new linear equation for v, we substitute back to find y, and there it is, our solution. Even with a cubic term and an equation that started out looking all wrong, our 5-step recipe still brought us home. So let's just take a step back and think about what we just did. We started with a whole class of equations that, at first glance, look totally unsolvable with our standard linear toolkits. But here's the big reveal. The Bernoulli equation was never really unsolvable to begin with. It was just a simple linear equation wearing a really, really good disguise. The whole key was learning how to see through that disguise by changing our perspective. So if you're going to remember anything, remember these 3 things. 1, spot that y to the n term. That's your clue. 2, remember your secret weapon, the substitution, v equals y to the 1 minus n. And 3, trust the 5-step recipe. It will guide you to the solution every single time. And really, this points to a much bigger idea, one that goes way beyond a math class. The most intimidating challenges we face often aren't solved with brute force, but with a clever shift in how we look at them. It kind of makes you wonder, right? How many other impossible problems out there are just simple ones in disguise, waiting for us to find the right way to look at them?